So we selected Mihai because he is one of the co-innovators of a very recent breakthrough in database-oriented systems, namely a completely new way of looking at incremental view maintenance, which is a fundamental problem in databases. And what Mihai and his co-authors, including Valtanen, did was to take a new look using digital signal processing. So Mihai, please take it away.
Well, is this on? Can I try again? How about now? Is it better? No. Can you hear me? Now it's on because the LED is on. Yes. Sorry. Well, oh yeah, this is good. Okay, so this is called DBSP, and it's a theoretical talk. I came here, I thought, Simon's is a theoretical institute, so I have to put some math. But I'm actually not a mathematician myself. But fortunately, the math is very, very simple, as you will see. If you want to know the details, there's a paper behind this. It was published in the last VLDB. All right, so this is all about motivated by incremental computation. So we'll start being informal, but we'll become mercilessly formal later. So let's say you have a program. And I apologize, I was under the assumption that you haven't seen Valtanen's talk 2 days ago, or that if you have seen it, you've liked it so much that you'd like to hear again some of the aspects in there. So let's say you have a program that computes something based on some input and gives you an output. And then let's say you have a notion of a change of your input. So you add something to your input, something small. And then let's also assume that often, if you change the input slightly, the output also changes slightly. So incremental computation means you want to reuse whatever you computed previously and not do the effort and just compute maybe ideally this change. So in general, there's a lot of very nice work about this, many PhD theses. It's very hard to define precisely, but there is one area where this works really well, and that's databases. And why? Because in databases, these programs P are what people call queries. And databases have a natural notion of a change. It's whatever you add or delete in a table. Usually a transaction is what we call a change, a set of changes in a set of tables. And also in databases, often databases are humongous, but they are continuously incrementally changed by adding and deleting rows in. And these changes tend to be much smaller than databases themselves. OK, so what is this about? DBSP is a very simple streaming language. It only has 4 operators, and I'm not going to even show all of them to you. And it's a pun. It comes from digital signal processing. I actually happen to have a master's in signal processing, which I never used for anything. So it was a shock to me that it actually is applicable in this domain. And then using this language, that's what is nice about DBSP is that using DBSP, we can define what it means precisely for something to be incremental. And they'll argue that incremental computation only makes sense in a streaming context. And then what is also very nice is that given an arbitrary DBSP program, we can generate automatically an incremental program out of it. So, and also, DBSP, this would be a cute thing, but also we have a recipe for implementing essentially anything you can write in a database language like SQL or even Datalog. We can implement any of these programs in DBSP. And as a corollary of all these facts is essentially we can incrementalize any arbitrary query that you can write in any language that people use in practice. OK, so this is the basic math ingredients. So we only need 2 ingredients, a billion groups. So every billion group, I remind you, is just a set with a plus, a minus, and a 0, which has some nice properties. We'll need it to be associative, commutative, and so on. And functions. And this is the entire base of this theory. This is a very simple algebra that is needed. And it's so simple, in fact, that one of our co-authors managed to fully verify all the theorems in the paper that we have. So we at least know that the theory is sound, and we have a hope that the implementation will also be correct. We have an implementation too. I'll only say a few words about it at the end. Now, the basic ingredient we're going to talk about is a stream. And think of a stream as an infinite vector indexed by time. Mathematically speaking, it's just a function from time, which I'm assuming it starts at some time 0, and giving you a value of some type A. Now, we'll put a very strong constraint, apparently, on the streams. We require all the values in the stream to be from some commutative group. OK, yeah, this is, again, useless. I'll show you that actually this constraint is not too bad in practice. It can be, in fact, it makes things much, much easier and is applicable in real databases. Then everything is a computation on streams. Streams operators are just functions that take streams and produce other streams. This is a unary stream operator. You can have binary stream operators. DBSP uses only very few kinds. We can write literally lots of functions on streams, but we use only very few of them. So all our functions are causal in the sense that they produce an output only based on the previous inputs they've seen, and they are time invariant. They are not allowed to keep a clock. So they have to, anyway, that doesn't matter too much. So this is all, by the way, these are all concepts that are very well known in the DSP literature, if you happen to be familiar with that. So how can we create stream operators? Well, the simplest way you can create a stream operator is by taking a scalar function and just applying it to every element of a stream. And this is called lifting. And in fact, mathematically, it's just function composition, because remember, streams are functions from time to values, and you just apply the function, you compose it with the stream function itself. Now, as a cute fact, the streams themselves, with the lifted operations of plus, minus, and 0, they form also a commutative group. So there will be commutative groups everywhere. OK, now this is one way you can create stream functions. And second way is you can take primitive stream functions and compose them. Let's say circuits and data flows programs, if you want. OK. Now, there is one interesting stream operator which is used a lot in digital signal processing, which is called the delay. And this name Z comes from something called the Z transform, which is actually a polynomial with coefficients associated with the stream values. But I don't want to go into that. So the description is really simple. If you have a stream of values, the delay operator will output a 0, and then your original stream. Looks simple, right? Well, just with these three ingredients, we can start building some very, very interesting computations. So anybody want to venture what this does? Well, you're not allowed to say anything. So let's look at it a little bit. So we have a stream. We delay it. We negate it and add it to itself. Right. So you can write a simple equation that the current output is the previous the current input minus the previous input. And this is nothing but a discrete derivative. So if you think of your stream as a continuous function of time, this is the discrete part of that. So what does this mean? Well, this is a very useful operator, so we'll call it D. And then if O is the stream, if you have an input stream of, for example, of numbers, then O, the output, is the stream of changes to those numbers. So each value is the difference between the current input and the previous one. Okay, so this operator also starts to compute deltas from values. All right, now even a simpler circuit, which looks a little bizarre, right? So we take a stream, and then we take its own output delayed and add it to itself. This seems to be like a recursive definition. And it is a recursive definition, but actually we can show easily that it's a well-formed one. Maybe I shouldn't have shown this yet. So the first output will be the first input because you get a 0. And then the tth output will be the current input plus the previous output, right? This is what this line says. And this is actually a system of equations which happens to be, it's like you can do a Gaussian elimination and get this unique solution. Every output is the sum of everything you've seen so far. And this actually is really nothing but the discrete form of the indefinite integral of the stream values, if you consider them as a function of time. This is a very useful operator, and it does the inverse of what the derivative did. If you give it a stream of changes, this is the previous stream of changes, it will give you back the original stream. And these operators are defined for any stream. They are total functions, and not only that, but they are inverses of each other. When you compose them, they give you nothing. So what does this have to do with databases? Well, let me make the first claim that all databases that you know of are streaming databases. So, MySQL is a streaming database. Why? OK, so let's take a database. What is it? It is a set of tables. And what is a transaction to the database? It's a change to the database. Now, the beautiful thing that people in databases have done is they said transactions are linearizable. So it means that there is a definite order in which the transactions could have committed. So let's take this order and let's call this a stream. This is the transactions that you have applied to your database in the order they have been applied to your database. All right, now to each of these transactions corresponds a snapshot of the database. So this is your initial database. This is the database after you have applied one transaction, two, and so on. What is the relationship between these two streams? Well, there's a very nice relationship that the database is the actual integral of the stream of transactions, right? How do you get to the third snapshot? You just apply the transactions, 0, 1, 2, 3. right? So it's a very, very simple relationship. So that's why I say that databases are streaming systems. By the way, yeah, question.
You assumed your operators were abelian, but database.
Excellent question. Excellent. So I'll answer that question in a second. Yeah. So I asked the database to be an abelian group, but databases are not abelian groups. But still, this works even if you have a weaker notion of a plus. Okay. Another thing, database views. So a database view is essentially a virtual function that you apply to your database. This is an example. Create some views function from some table in the database. What does it mean to create a view? Remember, we have a database is a sequence of snapshots. So it means that for every snapshot of the database, you have a snapshot, the corresponding snapshot of the view. So what this means is actually these views, the view stream, the views form a stream, the database form a stream, and the relationship between the two is the lifted query. The query is just a function, and this is the definition of what it means to lift a query. So views are lifted queries. So not only databases are streaming systems, but views are streaming systems computed by databases. Okay? So this is an equation on streams. DB is a stream of database snapshots. V is a stream of view snapshots. Okay, so now I will define what it means to incrementally maintain this view. So first of all, what we'll do is we'll compose the two definitions I gave you. Remember, I said that the database itself, as a stream, is the integral of a stream of transactions. So I just put these two diagrams together. And now I'll make it symmetric. I'll differentiate the stream of views. What will we get? We will actually get a stream of changes to the view. So this computation is always defined, no matter what the streams are. And given a stream of changes to your database will give you a stream of changes to the view. The view can be arbitrarily defined. And we'll call this the incremental view maintenance of the view. So this is slightly different from what database people call incremental view maintenance. They actually call this stream the incremental view maintenance. But I think this definition is much better for two reasons, at least. One is that because these are changes, we can hope that they are small. If your view is large, you have to query the view. So you'll do as much work to retrieve the data as you've done. So you won't save anything, really. Then second, it is compositional. Because both inputs and outputs are changes, then you can compose this kind of pipelines. And this is the fundamental sandwich of incremental view maintenance. It's a definition. We can argue whether the definition is right or wrong, but I think it's a very useful definition. So your query is sandwiched between a differentiator and an integrator. So keep this in mind. Now, if we just want to implement this, it's very expensive because you have to build a database, run the query, and then compute the deltas. But often, we can optimize this formula significantly. But I want to point out something very interesting. Most people who do incremental view maintenance, they try to compute the derivative of the query itself with respect to its inputs. Well, we don't need to do that. We only differentiate streams and integrate streams. And this is always defined. Notice is that we have no idea what this query does. This definition works for any query. So it's a very powerful definition. Okay, now there's two properties that makes this very useful. The first one is that if you have a chain of queries and you want to compute the incremental version, you can just incrementalize each of them. So then the proof is actually really simple, but I'll skip over it. The point is that this picture is the left-hand side. And then what you do is you insert this D and I pair, which cancel out. And then you regroup using function associativity, and then you get the right-hand side. So this is the entire proof. It's a proof by pictures. But this is actually very deep. It says that if you have a query, no matter how complicated, this is structural recursion. You can recursively decompose its subqueries and incrementalize them, and you'll get an incremental version of the entire query. So you reduce the problem of incrementalizing arbitrary queries to incrementalizing component queries. Another thing is if your operator is linear, remember these are operators over groups, so there's a notion of linearity, then the query and its incremental version are identical. And this is the top definition is this box, the bottom of the definition is this box, so there's a huge speed up between those two implementations. And this is important because most operators in SQL, for example, almost all relational operators are almost linear. And this works for recursive functions too. So you can do recursive queries. You can express fixed point on streams using circuits like this, and it works. Now, databases are not abelian groups, as you pointed out, but there's a simple trick which has been known for a long time using Z relations or Z sets. Essentially, you just put an integer weight on each row. And what a table just becomes a map with a finite support, which maps each row to an integer weight. And using this, you can essentially represent tables, multisets, and changes to tables. And this is actually an abelian group because it's a function that maps to Z, which is an abelian group. And you can do group by. Group by is actually this function, which, because this is an abelian group, this is also an abelian group. So you can do nested relations as well. And we can implement all of SQL. And moreover, we can implement it efficiently. So does it work? Well, actually, I, together with some colleagues, we quit our research jobs and founded this Feldera startup to try to prove that this is actually a viable technology. And we have open source implementations, the DBSP runtime in Rust, which implements primitives for all the operators that you have in a normal query language. And we have a full SQL compiler that generates code for this runtime. So we actually think it works. You can pass 7 million SQL logic tests, for example. So we can support the full SQL language, for sure. So this is the picture I want to leave you with. So databases, views, and streams, they are not foreign objects. Actually, in fact, you cannot separate them. They are just different projections of the same interesting mathematical object.
Okay, let's thank Mihai. So we have time for one question. Yes, Remy.
What's the mean when you go to a negative?
So the question is, what is a negative weight? Yeah, a negative weight essentially represents a deletion. So using Z-sets, we can represent not only tables, but also deletions from tables. So let me answer this question in a different way. I hope I have time to tell a joke.
How can I stop you?
Okay, so there's this question, a puzzle, like 2 people enter a house and then 3 come out. So different people have to explain what goes on, and the doctor says, obviously, they multiplied, there was a baby. And then, the sociologist says, yeah, there was somebody in the house. And then the mathematician says, one more person will go in and then the house will be empty. So that's exactly how Z-sets work, really. It's perfectly consistent.
Okay, folks, I think this is all the time we have. And let's thank the speaker. So this is the end of the first half.